Did you know that the simple stone you might kick on a path is older than all of human civilization? Stones are more than just rocks. They're tiny time capsules recording the history of our planet and even the entire universe. Each one has survived volcanic eruptions, shifting continents, and thousands of years of climate change. At first glance, they might seem ordinary gray, brown, maybe with a little sparkle, but they hide stories that go back billions of years. Their structure and chemical composition can reveal how our planet was born and how life on Earth changed. Stones aren't just for building or decorating gardens. They're geological and cosmic chronicles, silent witnesses to events we could never observe in our lifetime. Every layer, every scratch, and every mineral inside is like a page in a book about the Earth's history. Scientists use them to read the story of volcanoes, earthquakes, and the evolution of life itself. And sometimes, stones lead us to the stars. Some are meteorites that fell from space, carrying materials even older than our solar system. So, let's dive into the world of stones. They may seem quiet and still, but they're full of incredible stories just waiting to be told. So, what exactly is a stone? It sounds simple, but in geology, it's a fascinating concept. A stone isn't just a hard piece of stuff you find on the ground. It's a natural geological creation, made of minerals, formed by processes deep within the Earth's crust, sometimes billions of years ago. By studying them, we learn about our planet's history and the deep processes happening right under our feet. Now, geologists make a key distinction between a mineral and a rock. A mineral, like quartz or calcite, is a pure chemical substance with a specific crystal structure. A rock, on the other hand, is a collection of one or more minerals. Think of granite. It's a rock made of quartz, feldspar, and mica. Or coal, which is a rock formed from ancient plant remains. This distinction is vital because it helps geologists figure out what a rock is made of, how it formed, and what it's been through. The scale of stones is also incredible. They range from microscopic grains of sand to pebbles, boulders, and even gigantic rock masses that shape entire continents. And every single one carries information. A tiny grain of quartz can tell us about the formation of a sandstone from millions of years ago, while a massive granite block reveals the story of mountain building. So why are stones the foundation of geology? Because everything on Earth is built on rock processes. Rocks form the continents and ocean floors. They create mountains, valleys, and coastlines. By examining their layers and composition, scientists read Earth's history. They find records of ancient climates, earthquakes, volcanoes, and even life itself, preserved as fossils or chemical traces. Stones are also key to understanding what's inside our planet. By analyzing different types, igneous, sedimentary, and metamorphic geologists learn how continents formed, what ancient oceans looked like, and how Earth has cooled and heated over billions of years. Stones are not just objects. They are the keys to unlocking global geological mysteries. It's also important to remember that each stone is the result of natural forces colliding heat, pressure, erosion, water, wind, and even living organisms. This makes every stone unique. Even two fragments from the same rock can tell different stories. One piece might have originated deep within the Earth, while another was shaped by a river or volcanic lava. In short, a stone is a geological microcosm, a record of Earth's history, and a source of incredible knowledge. From tiny crystals to massive boulders, they are the foundation that allows us to understand the past, present, and future of our planet. Though they seem static, they are truly chronicles of time. Let's talk about how rocks are born. It's a process that shows just how dynamic our planet really is, even if stones seem motionless to us. One of the most important types of rocks is igneous rock, which forms when hot, molten material from inside the Earth, called magma, cools down and solidifies. This can happen deep underground, creating what we call intrusive rocks, or on the surface during a volcanic eruption, forming extrusive rocks. Igneous rocks are perfect examples of how the building blocks of continents and islands are made. Granite is a classic intrusive rock. It forms very slowly over millions of years, deep beneath the surface. This slow cooling allows large, visible crystals to grow. That's why you can see different specks of color in a granite countertop. Those are minerals like quartz, feldspar, and mica. Granite is incredibly hard and resistant, which is why it often forms the core of mountain ranges. On the other hand, you have basalt, which is an extrusive rock. Basalt forms when lava erupts from a volcano and cools rapidly on the surface. Because it cools so fast, there's no time for large crystals to form, so basalt is fine-grained and usually dark, almost black. Volcanic eruptions that create basalt are a dramatic reminder that our planet is constantly in motion, with hot magma from deep inside suddenly appearing at the surface to create new land. The difference between granite and basalt isn't just about looks. The slow-forming granite has large crystals and a varied composition, while the fast-cooling basalt is more uniform. But both tell a story of magmatic processes that have shaped Earth's crust for billions of years. Igneous rocks don't just tell us about eruptions, they also shape our landscapes. Granite forms majestic mountain peaks, while basalt creates vast lava fields, like those you see in Hawaii or Iceland. Of course, we use these rocks too. Granite is a popular choice for construction and sculptures, while basalt is used for industrial materials. By analyzing their composition, geologists can read their origins and understand what's happening deep within Earth's crust. It helps us understand volcanism, mountain building, and how islands are formed. So, every piece of granite or basalt is a witness to the powerful forces that have shaped our planet since its birth. Igneous rocks are really the beginning of the geological story, and they are the foundation for our entire understanding of Earth's history. Sedimentary rocks form another essential chapter in the story of stones and the history of the Earth. Unlike igneous rocks that burst forth from hot, molten material, sedimentary rocks have a much calmer origin story. They are born from tiny fragments of other rocks, minerals, or even the remnants of ancient life. Imagine these fragments accumulating over thousands or even millions of years. This process is like a slow, patient chronicle, with each layer recording changes in the environment, sea levels, climate, and the life that existed at that exact moment in time. So how do they form? Mostly, it happens when material gathers in water or gets moved around on land by weathering and transport. Think of sand, silt, and clay being carried by rivers, wind, or glaciers. They get dropped off in places where they can build up faster than they're washed away. Over immense stretches of time, the sheer weight of new layers piling on top squeezes the material together. Meanwhile, minerals dissolved in water act like a natural superglue, cementing all these grains into solid rock. This is exactly how we get sandstones, siltstones, and those classic layered shales. Let's take sandstone for example. It's a fantastic showcase of what we call a clastic sedimentary rock. It's made from grains of quartz or other minerals that settled in rivers, lakes, or oceans and were then glued together by minerals like calcite or silica. The color of sandstone can even tell you its story. Red hues, that points to iron. A brilliant white, probably pure quartz. And darker tones might hint at ancient organic matter mixed in. Then we have limestone, which is a bit different. It's a sedimentary rock that forms chemically or organically. Most of it is calcium carbonate, which can either precipitate directly from water or, more amazingly, come from the built-up skeletons of marine creatures like corals, mollusks, and tiny foraminifera. This means limestone isn't just a rock. It's a direct record of life. Its structure is often packed with fossils that whisper tales of ancient seas, water temperatures, and entire ecosystems from millions of years ago. It's no surprise that sedimentary rocks are absolute treasures for geologists, archaeologists, and paleontologists. Each layer of sediment is like a page in Earth's diary. It's a thin slice of time where climate shifts, natural disasters, and even traces of life are perfectly preserved. By analyzing these layers, scientists can reconstruct the movement of continents, ancient floods, ice ages, and even massive volcanic eruptions. Fossils locked in sandstone and limestone reveal how life evolved, and chemical analyses can even tell us what the atmosphere and oceans were like in the distant past. So, while they might look ordinary, sedimentary rocks are actually Earth's archive. They are a vast library of information about how our landscapes were shaped, how oceans and rivers shifted, what life flourished long ago, and how ecosystems responded to change. From sandstone to limestone, from clay to shale, every single piece is a witness to the processes that built our planet, layer by patient layer. And get this, they aren't static. They continue to erode, break down into new sediments, and become the raw material for future generations of rocks. It's all part of a grand cycle. Now, let's talk about the transformers of the rock world, metamorphic rocks. This is the third major category in geology, and they prove that stones don't just form, they can undergo incredible transformations, changing their entire structure and properties. Metamorphic rocks are created when existing rocks, whether they're igneous, sedimentary, or even older metamorphic ones, get subjected to intense heat and pressure. This process, called metamorphism, doesn't completely melt the rock like magma does. Instead, it reorganizes its internal structure, minerals, and texture, creating a brand new, often much stronger and more durable form. Marble is the quintessential example. It starts its life as limestone or dolomite. Deep within the Earth's crust, under immense pressure and high temperatures, it undergoes a process called recrystallization. The original calcium carbonate crystals transform into larger, shimmering calcite crystals. This is what gives marble its famous texture and beautiful sheen. It's valued not just for its looks, but also for its strength, which is why it's been a favorite for sculpture, architecture, and decoration for centuries. Another fantastic example is gneiss. Gneiss usually forms from granite or other igneous rocks that get squeezed and heated during the formation of mountain ranges. It's known for its distinct, layered or banded look, where minerals line up in parallel or wavy patterns. This structure isn't just pretty, it's geologically significant. It tells geologists about the direction of forces in the Earth's crust and the history of how mountains were built. The formation of these rocks is just fascinating because it shows that stones are anything but static. Magma, sediments, or older rocks can have their chemical and physical properties completely rewritten deep within the Earth, producing entirely new rocks with different visual and mechanical traits. Metamorphism can take millions of years and happen at depths from a few hundred meters to tens of kilometers, resulting in an incredible diversity of rock types. For geologists, metamorphic rocks are crucial because they hold clues about the extreme conditions they were born in. By studying them, scientists can reconstruct mountain-building events, the evolution of continents, and the history of crustal deformation. Analyzing the minerals in marble or gneiss lets researchers pinpoint the exact pressure and temperature the original rock endured, offering a window into tectonic plate movements. In short, metamorphic rocks reveal that stones are dynamic entities, capable of changing their very nature under the immense forces of our planet. Marble, gneiss, and others are not only beautiful and useful, but are also testaments to the powerful processes happening deep beneath our feet. So we've seen how rocks are born and how they can be transformed. This brings us to one of the most fundamental ideas in all of geology, the rock cycle. This concept explains that rocks aren't static objects, but are part of a continuous process of transformation that spans millions or even billions of years. Despite how permanent they seem, every rock igneous, sedimentary, or metamorphic is in a constant state of change. Think of the rock cycle as the life story of a rock. It begins deep within the earth and cycles through the surface and back again. The process often starts with igneous rocks. Magma cools deep in the crust to form granite, or flows to the surface as lava to become basalt. Once exposed to the elements, wind, water, ice, and temperature swings, these rocks start to weather and break down into smaller pieces called sediment. This sediment gets carried away by rivers, glaciers, or wind, beginning the next chapter, the formation of sedimentary rocks. Sand, silt, clay, and organic bits and pieces slowly pile up in basins. Over time, the pressure from layers above, along with natural mineral cements, turns these loose sediments into solid sandstone, limestone, or shale. But the story doesn't stop there. These sedimentary rocks can be buried deeper within the Earth's crust, where intense heat and pressure work their magic, transforming them into metamorphic rocks like marble or gneiss. The original sedimentary material gets a complete makeover, gaining new strength and a new crystalline structure. And even then, the cycle isn't finished. Metamorphic rocks, just like their igneous and sedimentary cousins, can be pushed back to the surface where they erode all over again, forming new sediments and starting the process of making new sedimentary rocks. Or they might be pushed even deeper into the crust, where they can melt back into magma, waiting to become a new igneous rock. It's a closed, continuous loop, with rock material constantly circulating between the Earth's surface and its interior. This cycle is more than just a physical process. It's our key to understanding Earth's entire history. It allows geologists to reconstruct ancient landscapes, volcanic eruptions, floods, ice ages, and the evolution of life itself. Every sedimentary layer, Every crystal in a piece of marble or granite tells us that rocks are in constant motion and that our planet is incredibly dynamic. To truly understand rocks, we have to look at what they're made of: minerals. Minerals are the real heart of geology. They're the building blocks that give every rock its unique character, its hardness, color, luster, and chemical properties. From a tiny grain of sand to a massive block of granite, every rock is simply a collection of minerals. By figuring out which minerals make up a rock, geologists can read its entire history, from how it formed to the environment it was born in. Every piece of stone is a witness to a story that never ever ends. Have you ever picked up a stone and wondered what it's made of? What gives it its unique color, its strength, its sparkle? The answer lies in minerals, the tiny building blocks that tell a stone's entire story. The color of a rock is a direct reflection of its mineral content. Take granite, for example. It can be pink, gray, black, or nearly white, all depending on how much feldspar, quartz, and mica it contains. Quartz gives rocks that light, glassy shine, while feldspar adds shades of pink, red, or even green. Then you have micas, like biotite, which sprinkle in those shimmering flakes that catch the light so beautifully. Hardness is another mineral story. Quartz is one of the toughest common minerals out there, which is why quartz-rich rocks are so resistant to erosion. Feldspar is a bit softer, making rocks more likely to fracture and break down over time. And micas, though soft, are surprisingly tough against water and temperature changes, which is why they keep their sparkle in many different rock types. And then there are the geological treasures, rare minerals. They can give rocks the most unique colors and properties, making them incredibly valuable. Think of sapphire, ruby, and emerald. These are just rare forms of common minerals that produce stunning brilliance. Or malachite and azurite, which are copper minerals that create those intense green and blue patterns you see in some rocks, turning them into natural works of art. Minerals don't just define a rock's appearance. They also determine its use. Quartz is essential for making glass and ceramics. Feldspar is used in porcelain and building materials. Mica is a key ingredient in electronics, insulation, and even cosmetics. And many rare minerals are vital for advanced technologies, from semiconductors to chemical catalysts. So every stone you see, whether it's a huge boulder, a smooth beach pebble, or a marble statue, is a complex puzzle of minerals. They give each stone its unique identity, its color, hardness, and geological history. Through minerals, stones become not just silent witnesses to Earth's past, but also incredible resources that have fueled human knowledge and creativity for thousands of years. Each fragment of stone is a tiny universe of chemistry and physics, a testament to nature's incredible precision and diversity. Stones aren't just beautiful objects to admire. They are the very foundation of life on our planet. Their presence and properties shape everything from the continents we live on to the air we breathe. Understanding their role reveals just how deeply geology, climate, and life are connected. First, think about the Earth's crust, the rigid outer layer where all life exists. This layer, known as the lithosphere, is made of rock. The continents are built on granites and gneisses, while the ocean floor is mostly basalt. These rocks provide the stable yet dynamic platform upon which our entire biosphere rests. Continents drift, mountains rise, and valleys are carved, all because of the behavior of these massive rock formations. Soils, the very basis of plant life, also come from rocks. Through a process called weathering, rocks are broken down into smaller and smaller pieces. These fragments mix with organic matter to create the fertile ground that feeds our world. Different rocks create different soils. Sandstone, granite, or limestone each contribute a unique mix of minerals, influencing the soil's pH, its ability to hold water, and its nutrient content. This geological diversity is why we have such a rich variety of ecosystems and biodiversity across the planet. Rocks also play a crucial role in our water supply. Porous rocks like sandstone and limestone act as giant natural sponges, storing vast quantities of groundwater in underground reservoirs. These reservoirs feed our rivers, lakes, and wells. Water can travel for miles through cracks in rocks, sustaining ecosystems even in dry regions. In this way, stones are not just the foundation of the land, but also the guardians of our most precious resource, water. And let's not forget the dramatic geological processes that shape our world. Volcanoes create new land and islands, and their eruptions release minerals essential for life. Erosion, phenomenal by water, wind, and glaciers, carves out canyons, valleys, and plains. Tectonic forces push rocks upward to form mountains, which in turn influence local climates and weather patterns. Every single stone, no matter how small, is a participant in these planet-shaping events. Finally, rocks are the source of essential elements for life. As they weather, minerals release calcium, magnesium, potassium, and iron into soils and water. These are the nutrients that plants need to grow and that animals and humans need to survive. Without this slow, steady breakdown of rocks, the chemical cycles that support all life on Earth simply wouldn't exist. So stones are far more than just hard, lifeless objects. They form our planet's crust, create our soils, manage our water, shape our landscapes, and supply the very elements of life. Every stone is a quiet, irreplaceable hero in the story of our living planet, showing us that geology and life are truly one and the same. The connection between humans and stones goes back to the very dawn of our existence. For our earliest ancestors, a stone wasn't just a part of the landscape, it was a tool, a weapon, and an extension of their own hands. It was the first durable material that allowed humans to shape their world, find food, and survive. The oldest stone tools, dating back over 2 million years, were simple but incredibly effective. Sharp flakes of rock were used to cut meat, crack open bones, and shape wood. Even a small, sharp piece of stone gave our ancestors a huge survival advantage, helping them secure food and defend themselves. Stone was humanity's first multi-tool, basic but revolutionary. As time went on, people learned to choose specific stones for specific jobs. Hard, brittle flint was perfect for creating sharp edges. Tougher rocks like basalt were used for hammers and axes. Softer stones like limestone were used for grinding. This wasn't just practical. It showed a growing understanding of the natural world, a knowledge of which materials were strong, which could be shaped, and which were best for certain tasks. Stones were also key to developing early survival skills. A sharpened stone tip made hunting possible. Striking flint against iron-rich minerals created a spark, giving us fire. Larger stones served as anvils for crafting other tools. They even became the canvas for our first art and communication. Rock carvings and ancient symbols etched into stone surfaces are the lasting records of prehistoric life, telling stories across millennia. But stones weren't just functional. In many ancient cultures, they held deep ritual significance. Stone circles, standing stones, and ancient altars show us that our ancestors saw more than just utility in them. They saw meaning. Stones became landmarks, gathering places, and powerful symbols connecting people to the cosmos, the landscape, and each other. From our earliest days to our modern world, stones have remained one of humanity's most important building materials. They have shaped our cities, our architecture, and our greatest works of art. Their strength and variety have made them not just a practical resource, but also a symbol of power, beauty, and permanence. Ancient civilizations understood the incredible qualities of stone. The Egyptians used massive blocks of granite and limestone to build the pyramids and temples that still stand today. Transporting and placing these stones with such precision shows their advanced knowledge of engineering. Stone didn't just ensure longevity, it conveyed a sense of grandeur and power. In classical Greece and Rome, stone was the foundation of civilization. They mastered working with marble and travertine to create the stunning columns, sculptures, and buildings that we still admire for their perfect symmetry. Marble, with its smooth, lustrous finish, became a symbol of luxury and permanence, all while being incredibly practical and resistant to the elements. From the Middle Ages, stone was the undisputed king of construction. Think of the mighty castles and towering cathedrals. Granite, sandstone, and limestone weren't just chosen for their strength. They were a statement. Heavy defensive walls protected entire communities, while Gothic cathedrals used stone not just for support, but for art. Their soaring arches and intricate ornamentation turned buildings into monuments of faith and power, showing how a single material could be both functional and breathtakingly beautiful. As technology advanced, so did our use of stone. In the 19th and 20th centuries, materials like granite, marble, and travertine adorned grand public buildings and monuments. Combined with new inventions like concrete and steel, stone helped architects push the boundaries of what was possible, creating the modern cityscapes we know today. Even now, stone is prized as a cladding and decorative material, lending a sense of prestige and permanence to our homes and offices. It connects us to a long history of strength and beauty. But what does it really mean to study a stone? It's like learning to read the Earth's autobiography. Every stone is a geological chronicle, and geologists are the interpreters of this ancient language. Their work takes us on a journey through billions of years, revealing the processes that shaped our planet, its climate, and life itself. The adventure begins in the field. This is classical geology, where scientists study rocks in their natural habitat. With a geological hammer, a hand lens, and a compass, they learn to identify different rock types, textures, and mineral compositions just by looking. They observe how layers are arranged, check for fractures, and test for hardness. This initial classification is the first crucial step to understanding the history of a landscape. Next, the samples go to the lab, where the real detective work begins. Under an optical microscope, geologists can see the hidden world within the rock, the intricate arrangement of crystals and grains. Electron microscopes zoom in even further, revealing tiny mineral inclusions and traces of chemical changes that are invisible to the naked eye. Then comes chemical analysis. Techniques like mass spectrometry tell scientists the exact chemical and mineral makeup of a stone. This data can reveal where the rock came from, the environment it formed in, and the powerful geological forces it has endured. But one of the most groundbreaking tools is radiometric dating. By measuring the decay of radioactive isotopes like uranium or carbon, scientists can determine the age of a rock with incredible precision. We're talking millions or even billions of years. This allows them to create a timeline of Earth's history, pinpointing major events like volcanic eruptions, the rise of mountain ranges, or ancient ice ages. It even helps them place fossils in their correct time period, giving us a clearer picture of the evolution of life. So why is all this so important? Because stones aren't just dead matter. They are carriers of information. Their structure, their minerals, their layers, each detail is a page in a book documenting billions of years of history. Thanks to these scientific methods, we can read the story of how continents formed, how oceans rose and fell, and how life itself emerged and evolved. It's a journey from the grand scale of mountains and valleys, right down to the atomic level. Every rock is an archive, and geologists are the detectives of time, deciphering its secrets. Now let's explore some of the most mind-blowing facts about stones. They are far more than just the foundation of our planet. They are full of surprises that can seem almost magical. Did you know that the oldest rocks on Earth are over 4 billion years old? These are fragments of our planet's original crust, survivors of countless volcanic eruptions and tectonic shifts. Studying them is like opening a time capsule from the dawn of our world. Every crystal inside preserves a snapshot of the young Earth's environment, offering clues about the conditions that led to the very first sparks of life. And get this, some stones are still growing. In geothermal springs, deep caves, or on the ocean floor, minerals are slowly crystallizing out of water. This is how stalactites and stalagmites form, one drop at a time. These processes are incredibly slow, but they are living proof that rocks aren't static. Under the right conditions, they can create complex and fantastical structures that continue to evolve. Stones can also be biological archives. Trapped within sedimentary and metamorphic rocks, scientists find microfossils, ancient algae, bacteria, and other microorganisms preserved for millions of years. These tiny remnants allow us to study the evolution of early life and reconstruct the climate of distant epochs. Each fragment is a window into Earth's deep past. And some stones aren't even from Earth. I'm talking about meteorites. These are fragments of asteroids, planets, or moons that survived a fiery journey through our atmosphere. They can contain minerals that don't naturally exist on our planet, giving us invaluable information about the formation of our solar system and the cosmos beyond. They prove that stones tell stories not just of our world, but of the entire universe. The wonders don't stop there. Certain crystals like quartz have piezoelectric properties, meaning they can generate an electric charge under pressure. This is why quartz is used in watches and electronics. It's a perfect example of how a geological wonder can become a cornerstone of modern technology. Stones also impress us with their sheer scale. The largest boulders ever moved by natural forces weigh thousands of tons. Many of these are erratic boulders, giant rocks carried for hundreds of miles by ancient glaciers. Their presence is a humbling reminder of the immense power of geological processes, which operate on a scale far beyond our human experience. Finally, consider their resilience. Stones can survive the most extreme environments imaginable. Volcanic rocks solidify from lava hotter than 1,000 degrees Celsius. Marbles and gneisses form under immense pressure deep within the Earth's crust. Sandstones and basalts withstand the constant, grinding erosion of the oceans for millennia. Their incredible durability is what makes our planet stable. So the next time you see a stone, take a moment. It could be a 4-billion-year-old witness to history, a growing crystal, a carrier of ancient life, or a traveler from the stars. They are not just the foundation of our world. They are a source of knowledge, inspiration, and endless wonder. Every single rock is a miniature laboratory and a chronicle of the universe, waiting to tell its story. Thanks for joining me on this journey through the world of stones.